Having now talked about rates in epidemiology, let's go on to talk about particular types of rates. And by that I mean incidence and prevalence rate. Definition first here. Incidence rates, we're talking about the number of new cases in a population divided by people at risk to be a new case in the same population in the same time frame. Prevalence, by contrast, we're talking about all cases divided again by people at risk to be a case in the same population in the same time frame. Notice, first, for incidence and prevalence, you have to be talking about numerator and denominator from the same population, and secondly, it has to be within the same measurement time frame. How do we distinguish them? Well, they're measuring different things. Incidence, it's only the new cases, the onset that we care about. Prevalence, it's all cases, whether new, old, or anywhere in between that we care about. Incidence, new cases only. Prevalence, all cases. Now notice something. Both incidence and prevalence are divided by risk, but risk is different for incidence than it is for prevalence. Risk for incidence is risk to catch or acquire the disease. Risk for prevalence is risk to have the disease. And here's the crucial differentiating issue. If I have the disease already, I'm of course not logically at risk to catch the disease. Having something precludes me from being able to be the onset. On the other hand, if I have the disease already, I am of course at risk to have the disease. If we're playing ball back and forth and you toss me the ball and I'm holding it, I'm not at risk to catch the ball. Why? Because I'm already have it in my hand. On the other hand, I am at risk to have the ball because, again, I have it in my hand already. Risk for incidence is risk to acquire, that is, begin the disease. Risk for prevalence is risk to have the disease. A simple metaphor should help you conceptualize what I'm talking about here. Picture a room such as this one with people milling around inside. Picture a door leading out into a hallway where there's a lot of other people milling around. Everyone that walks through that door into the room during the measurement period, those are the incident cases, the onset, the new people coming in. Prevalence. Prevalence is everybody who walks through the door into the room, but also includes everybody already in the room, including anyone who's in the room who walks back out again. If you're in the room at all, even for a nanosecond during the measurement period, you count as a case of prevalence. The only people that count for incidence are people that traverse, that is, enter the room from the outside. You need a little mnemonic to help you remember these? Well, look up here at the spelling. Look at the word incident. Look at the first two letters. First two letters spell the word in. These are the new cases, the cases coming in, as it were. Prevalence. Well, that's just the other one. I can't really do much for you there. All right, look, if you're a really, really poor speller, you look at prevalence and look in the middle and see AL and say, hey, that spells all. Well, no, it doesn't. That's a failed presidential candidate. But hey, if it helps you remember it, I don't particularly care. Incidence, new cases only. Prevalence, all cases. Now, there's some other terms I want you to associate with incidence and then prevalence. With incidence, I want you to associate it with the term attack rate. An attack rate is simply a special type of incidence rate. Think about incidence rate as the overarching category, which attack rate is simply one subspecies. An attack rate is an incidence rate where I further shrink the denominator for some known exposure. We're not looking at all the people that are at risk, but just the people that have this particular exposure. An example should clarify this. One Saturday evening, 100 people go out to eat at a local Italian restaurant. Of those 100 people, 50 order calamari. Of the 50 people who order calamari, 30 become ill with food poisoning. What's the general incidence rate for food poisoning at the restaurant? Oh, that's easy. 30 divided by 100, because we're going to take everybody at the restaurant as being at risk. What's the attack rate for calamari? Oh, that's easy. Once again, now 30 divided by 50. Notice the difference between the general incidence rate, where all the patrons are included, and the attack rate, we're only going to look at the people that had that particular food. Now, if you're confronted with a foodborne outbreak on the exam, as you have been in the past, and you need to decide which food is most likely the source of the outbreak, it ought to be clear now how to answer that question. You're going to simply compute an attack rate for every food, and the food that generates the highest attack rate is the food most likely to be the source of the outbreak. Turn your attention down to prevalence. Let's talk about two different types of prevalence, point prevalence and period prevalence. Here, the issue is the measurement time frame. When we're talking about point prevalence, we're talking about measuring who has the disease divided by people at risk to have the disease at a single moment in time, at a single instant in time. Not this year, but right now who has it divided by people at risk. Period prevalence, by contrast, is about a span of time, a week, a month, a year, a lifetime. You often see these two numbers side by side in your text. For example, if you page through Harrison's, you'll find that for men, secondary impotence has a point prevalence of 3% and a lifetime prevalence of maybe 23%. Notice that point prevalence is smaller than lifetime prevalence. Well, come on, of course it is. Because the wider the time frame in which I'm looking for cases, by simple probability, the more cases are likely to appear. Point prevalence is a single moment in time. Period prevalence is across a span of time. Now, as we're going on to our next set of issues, I have a few simple questions for you. Suppose I want to track the course of influenza as it traverses the United States, influenza as it travels across the United States. Should I be concerned with incidence or prevalence? Well, the right answer, of course, is incidence, because for any acute condition, influenza is an acute onset, we're concerned about the beginning, the onset of the disease. Incidence is what matters. Suppose, by contrast, I was interested in tracing diabetes as it traveled across the United States over the next several decades, diabetes in the United States. In that instance, I'd be more concerned with prevalence, because it's not the beginning, it's the having that I want to measure. I mean, consider the incident question. How many people acquire diabetes today? It's even hard to deal with the incidence issue when we talk about a chronic condition such as diabetes. Two other simple terms, morbidity and mortality. Morbidity, of course, is illness. Mortality, of course, is death. When I'm talking about morbidity, I show you morbidity data, illness data. What am I talking about? Incidence or prevalence? Well, answer, of course, is could be either one. I could talk about the onset of disease, or I could talk about having the disease. If you see disease data, you have to read your question carefully and see what was done. Is it incidence or is it prevalence? By contrast, let's talk about mortality data. Mortality data, we're talking about death. We're talking about mortality. Is that incidence or prevalence? Well, right. It could only be incidence data. Because of mortality, we're not counting the number of dead people, we're counting the onset of death, the newly dead, the beginning dead. So that's by definition incidence data. You now know whenever you see a table of mortality data, we're talking about incidence data. So mortality data is by definition incidence data. Having talked about incidence and then prevalence as separate concepts, I now want to link them together for you. I now want you to understand how they're related to each other. We talk about this relationship in two distinct ways. First, we have the so-called conceptual formula. Conceptual formula reminds us that P, prevalence, is equal to I, incidence, times D, duration. Prevalence is a function of incidence times duration. This conceptual formula helps you remember the direction of relationships, but please do not treat this with full mathematical certainty. That is, I don't want anyone to ever come to me and say, hey, I can take prevalence and divide by incidence and that will give me duration. No, you can't really do that. Nor can you take prevalence and divide by duration to give you incidence. You can't really do that either. These are measured on different metrics, and when you put them together, since they're on different metrics, you don't get a clean, clear answer. What you can do with this simple formula, though, is remember the direction of relationships. You can remember that, for example, as incidence increases, therefore prevalence increases. Or as duration goes down, people have the disease for a shorter amount of time, then prevalence goes down as well. On an exam question, if you want to change prevalence, you do so by changing incidence up or down, or duration up or down. The second way we like you to think about this relationship between incidence and prevalence is with the so-called prevalence plot diagram, a version of which you'll see in your syllabus, and a slightly different version of which I have here on the slide. We're laying out here for you a visual metaphor, a way of thinking about these relationships. So let me go through and describe the metaphor, and then I'll go back in a moment and label the pieces. We have first a reservoir that contains water or indeed your favorite beverage. Over time, that water runs through this pipe, and then becomes deposited in this tub or basin. Now the basin would overflow, except there's two drains. One over to the right, which is down in the sewer, never to be seen again. One to the left, which is basically recycling, where you now go back in the general reservoir, where you can once again flow through the pipe. And what you need to have here is a sense of flow. See the water coursing through the system. Yes, it's a static line drawing, but you have to supply the animation in your own brain here. Let's go through now and label the pieces. In the reservoir, well, this is the population at risk. Not the people who have the disease, remember, but the people who could have the disease, potential cases. When they do get the disease, that's running through this pipe, and since they're getting the disease, they are onset. These are the incident cases. Over time, the incident cases accumulate in the so-called prevalence pot. As the diagram reminds you, there's two and only two ways to cease to be a case of prevalence. One, you die. If you die, you're not a case anymore. Dead people simply don't count. We don't focus on them. The other way you cease to be a case of prevalence, of course, that's easy. You recover. When you recover, what does that mean? Well, it means you go back into the general reservoir where you're now once again at risk to be a new case of incidence and prevalence. And once again there, you have the sense of a cycle. One thing changing to the other, risk to incidence to prevalence, and then back again. Although, again, it's a static line drawing, you have to supply the sense of dynamism, the sense of motion, the sense of change across time. Now, I like this diagram quite a bit. I use it a lot when I'm trying to instruct you about these concepts. Well, let me talk about what's going on here. First, I like this because it gives you a sense of incidence and prevalence in terms of this dynamic, changing world out there. But there's a more basic reason. Do you ever wonder why they test you so much on epidemiology and indeed biostatistics on your Step 2 CK, and by the way, your Step 1 and your Step 3 exam as well? Well, the reason why they keep testing you on this is they're really testing the details to make sure you grasp one overarching concept. What's the overarching concept? Simple. Here it is. Numbers are not reality. Numbers, all the numbers you will see in medicine, all the numbers that make up medical practice are not reality. They are measurements of reality. And the key, dare I say important intellectual point, is to realize that the numbers themselves are not what the reality is. Reality is something else. The numbers are merely our measurement. Remembering that every measurement is reality, that is truth, plus error. And so every measurement is an approximation, but not an exact reality. Your job as a physician is to take in the numbers you will see, and then not simply stop with the numbers, but envision the dynamic reality in the world out there that produced the numbers in the first place. We want you to act on that dynamic reality, not simply act to change the numbers. Numbers are not the reality. The reality is something else. You have to have the X-ray vision to see through the numbers to the reality that produced the numbers in the first place. This diagram is a way to get you to, in a concrete way, come to grips with that. Let's look at for a second. Incidence and prevalence. As soon as we measure these numbers in this dynamic, changing universe, the numbers we measure are now wrong. Incidence is merely a measurement, but the reality continues to change. Prevalence is a mere measurement, but reality continues to change. The point about this is to get you to think not in terms of the numbers, but in terms of the real dynamic system that produced those numbers in the first place. Let's go on now to talk about one additional concept. Number needed to treat. This one's a little bit slippery, and the real problem is the name is misleading. See, number needed to treat, NNT, sounds like we're talking about treatment, and the point is we're not. A better name would be number needed to prevent, because NNT is not about treatment, it's about prevention, although I'm going to call it what we always do, number needed to treat, so you're familiar with the term. The setup here is simple. How many people do we have to go out and do something to in order to stop a single case of disease from occurring? Now, I know that's an odd metric, but accept that from me. How many people do we have to do something to stop one case of disease? Well, if you think about that just for a moment, that means that ought to be fairly closely related to the incidence rate, don't you think? Because if a whole lot of people are catching the disease, doing a little bit should still stop one case. By contrast, if hardly anyone is acquiring the disease, then we have to go out and touch a whole lot more people in order to stop one single case of disease. So number needed to treat is related to the incidence rate. Now, here's how it is related. It's the inverse of the incidence rate. Inverse, the mathematical inverse. Simply you take the numerator, take the denominator, flip them, and incidence rate becomes number needed to treat. It's really that straightforward. Let's do this concretely. If the incidence rate is 1 per 1,000, what is number needed to treat? Well, that's easy. In general, for every 1,000 people I give a vaccine to, I will stop one person from getting the disease. If the incidence rate is 1 per 1,000, for every 1,000 shots, I stop one person from getting the disease. Number needed to treat is 1,000. Now, I know that's intuitive, or at least I hope it is, but let's stop, slow down, and go back over the mechanics of how we got there. We took 1 per 1,000, flipped them, became 1,000 divided by 1, and hence you can simply say that as 1,000. Hold on to those mechanics. Let's change the numbers. Suppose incidence rate is 50 per 1,000. What's number needed to treat? Once again, 50 now goes on the bottom, 1,000 goes on the top, and when you reduce it down, number needed to treat comes to 20. Roughly for every 20 people I give a vaccine to, I will stop one person from acquiring the disease. What are the things to remember here? First, number needed to treat is not about treatment, it's about prevention. We're talking about stopping people from getting the disease. That tells you it's related to the incidence rate, and related in a direct way, it's the inverse of the incidence rate. You simply take numerator, denominator, and flip them, and you have your answer. If we have an incidence rate of 50 per 1,000, doing the inverse ends us with 1,000 divided by 50, reduces down to 20. For every 20 people I give shots to, I stop one case of disease. Now please notice, suppose I told you number needed to treat was 20. Could you give me the incidence rate? Well, if you think for a second, yes you can, because 20 is really 20 over 1. And we simply take the inverse of that, now 1 on top and 20 on the bottom, and then we can just multiply that out to get to whatever ratio you want. If you want to get back to where we started from here, you multiply it out to get to 50 out of 1,000. Multiply top and bottom by 50, and you get to 50 divided by 1,000. So you now notice that you can not only get from incidence rate to number needed to treat, but you can get from number needed to treat to incidence rate, one way or the other way. Having been over these basic concepts, let's try some application issues. I'm going to go over some of the presented material that's in your syllabus. Let's try question 4, for example. Now, question 4 is nice USMLE format, although it's not really a particularly hard question, but let's see what you do with it anyhow. I'll begin to read. A pharmaceutical corporation completes trials on a vaccine for a severe strain of influenza virus, demonstrating high vaccine efficacy. The Food and Drug Administration approves the vaccine for use in the United States. As the influenza pandemic approaches U.S. borders, the Centers for Disease Control and Prevention launches a nationwide campaign to vaccinate the population using local public health department personnel throughout the country to ensure the vaccine is available free of charge to all people. Assuming that a high degree of vaccine coverage is achieved, what is the expected impact of this major public health initiative? If we give a lot of people a vaccine, what's that going to do to the general population? Well, we have 5 choices. Let's do them in order. A, decreased duration of influenza illness leading to decreased prevalence. Decreased duration leading to decreased prevalence. Well, there's a vaccine. Vaccine doesn't shorten the amount of time you have the disease. Vaccine, if it works, stops you from getting the disease. So we don't really know anything about duration. A can't be the right answer. How about B, decreased incidence of influenza illness leading to decreased prevalence. Now that looks good, because the vaccine should shrink incidence and hence prevalence should go down as well. But to make sure we have the best answer, let's make sure we check the other 3 options. C, decreased incidence offset by increased duration. Well, I know nothing about duration, so I'm not going to pick that one. D, no change in observed incidence or duration, no change in prevalence. Well, I know good vaccine makes incidence go down, so that can't be right. And finally, the effects on prevalence cannot be determined from the information given. Sure they can. If incidence goes down, prevalence goes down. And so the answer is what we thought it was. The answer is B, mark it, and time to move on. You have a different form of a question as you turn the page. This question provides you some text and then a graph summarizing some information that are pertinent to the text provided. Now, this next exam strategy issue is important. We discover when we give you graphs in exam questions, you tend to focus on the graph and you don't always read the text that accompanies the graph. I have to tell you, the text is absolutely critical for you because the text provides the context for everything that goes forward. So I'm going to begin not by looking at the graph, but by reading the text. Among 245 college students who dedicated 1 month of summer break to building homes for Habitat for Humanity, 12 developed back strains on the job. Based on the diagram of these 12 episodes of back strain, answer the following questions. Okay, so now we know we're looking at back strain for people that did work for Habitat for Humanity. As we look at a graph, we see two vertical lines. The first one on the left, July 15th, and the second one on the right, July 31st. There is a 2-week period, therefore, between the two lines. We also see back strains, if any, plotted there for these 12 individuals. And the way to read this is the beginning of the little bar is the onset of the back strain. The width of the bar, that's the duration of the back strain. And when the little bar ends, that's the terminal event, when there is no more back strain, when the patient, in short, got better. Onset, duration, terminal event. You have to make sure you can read the graph. All right, with that in place, let's go down and answer the series of questions provided. Number 6. What is the point prevalence rate on July 15th? Point prevalence rate on July 15th. Well, that means the first vertical is all we're going to look at here. So let's see. It looks like E and K cross that first vertical. Therefore, my numerator is 2. But note, 2 is not the answer, because everything in epidemiology is, of course, a ratio. 2 is the numerator. I now need to add the denominator to get myself to the answer. It's 2 out of what? Well, that's fairly easy. Everybody here that worked for Habitat for Humanity is at risk for back strain. So therefore, 2 out of the number up on top in the text, 245. 2 out of 245 is the answer. Next, number 7. What is the point prevalence rate on July 31st? Now we're talking about the second line over on the right. Now we have B, G, and I crossing that line. That looks like 3. So my numerator is 3. But again, numerator is only half an answer. We need the denominator as well. 3 out of what? Well, looks to me like everybody's at risk here. So 3 out of 245. 3 out of 245, fairly straightforward. Everybody's at risk. I just have to make sure I have 245 for the denominator. The answer is E. What is the incidence rate? New question now. The incidence rate for the period of July 15th to July 31st. Incidence rate, July 15th, July 31st. We're counting onset only. Only the beginnings of the bar are what we want to focus on. By my read, it looks like A, B, D, F, G, I, J, and L all have onsets, that is, beginnings within that specified period. That's 8 individuals. Please notice I would not count C, the onset is outside the specified period, nor would I count E, H, or K, because their onset is outside the specified period. I now have a numerator of 8 for incidence within that specified period. 8 divided by what? Well, once again, looks to me like everybody's at risk here. It's going to be 8 divided by 245. Fairly straightforward. But, you know what? Let's change your graph just a little bit. Take a look at G. Instead of G as it is here, I'm going to make G the following. G is now a much longer bar. I've extended it over towards the left. Let's once again go answer question 8 about the incidence rate for that period, July 15, July 31st. So now, looks like A, B, D, E, I, J, and L. It looks like 7. The numerator is 7. Okay. 7 divided by what? Yep. Wait, not 245 this time. See, G has the back strain the entire time. Since G has the back strain the entire time, G cannot acquire, that is, begin to be a case of back strain. Therefore, G is not at risk. Translation, take him out of the denominator. Instead of 7 divided by 245, the right answer is 7 divided by 244. I'll say that again, 7 divided by 244. We take G out as at risk, therefore 244, not 245. I'm going to return your diagram to the state it was originally as we answer the last of these questions, number 9. Number 9, what is the period prevalence for the July 15th through July 31st? Once again, between the two verticals, what is the period prevalence? Now, anyone that has any part of the bar within that period gets counted for our numerator. So that's A, B, D, E, F, G, I, J, K, and L. Looks to me like 10 individuals. 10 is my numerator then when I'm talking about prevalence. 10 out of what? It's easy once again. Everyone's at risk. Therefore, 10 divided by 245. So that was fairly straightforward because risk for a back strain is fairly straightforward and easy to understand. But you know what? Let's change the question. If we change the disease we're talking about, we can change the question answer as well. Okay, so let's now shift a little bit. Keeping the same graph, instead of having it be back strain, let's look at the same information but talk about it as measles. Now measles, of course, is different than back strain because, well, when you get over measles, you're not going to get it again. Measles have conferred immunity, and this conferred immunity changes the meaning and therefore the answer here. Let's go through our 4 questions again, this time looking at it in terms of measles. Number 6, what is the point prevalence rate for measles on July 15th? Well, E and K, the numerator is still 2, but now the denominator's got to shift because H, having gotten measles and gotten over it before we come to that period, is no longer at risk. Therefore, it's going to be 2 divided by 244. Not 245, but 244. Why? H has immunity, therefore no risk, therefore we drop him out of the denominator. Number 7, what is the point prevalence rate on July 31st? Once again, the numerator is the same as before, B, G, and I, that's 3, but now 3 divided by what? Well, as I read this, A, D, E, F, H, J, K, and L all have measles and then get over the measles prior to this point of time where we want to do our measurement. Therefore, 8 people have measles and got over measles before we come to this line. Therefore, 8 of these people are not any longer at risk. Our denominator, therefore, is not 245, but 245 minus 8, or 237. The right answer for point prevalence for measles on July 31st is 3 divided by 237. Let's go do number 8. Once again, measles. What is the incidence rate for measles in the period of July 15th to July 31st? Well, the numerator, again, is going to be the same. Still going to be 8, because the 8 onsets we still have. But now 8 divided by what? Well, as I read this, H is not at risk to be a new case of measles, but neither are E or K. H got over the measles before the period starts, hence cannot acquire, but E and K got them before it starts, then got over the measles, and then here afterwards were not at risk to be a new case. Therefore, E, H, and K, 3 of those are subtracted out, and it becomes 8 divided by 242. 8 divided by 242 because E and H and K are not at risk for measles. That is, not at risk to be new cases of measles, not incidence risk. Number 9, what is the period prevalence, again for measles, July 15th to July 31st? Once again, the numerator stays the same, does not change. 10, just as before, but 10 divided by what? Not 245, but 244. Who's the one person we're going to exclude? We're going to exclude H. H had measles, got over it. Now H is not at risk to have measles. Please note, for prevalence, E and K are in fact counted, not only in the denominator at risk, but in the numerator because they in fact have it during the period. Please note that C, which occurs after the period, is counted as at risk. We don't count C as having it during the period, but we do count C as at risk across the period. If we're talking about measles here, therefore, the answer is again 10 divided by 244. The point of this exercise is to walk you through exactly what we're talking about when we're using the concepts of incidence and prevalence. And notice how this question confronts you. If you memorize the terms and definitions exactly, but you can't apply them in this simple presented set of data, they don't want you to get the question right. USMLE Step 2 CK exam is not about regurgitating information memorized. It's about problem solving what's presented with the information that you already have in your head.